Can the online people still hear me like that? Can the, since we've just switched the microphone, and yes, so that's good. Can the physical present on-prem people hear me? Awesome, thank you. So it's now 9:14. That means 1 minute early for PT, but I will start anyway. The segment will be 90 minutes more or less, which should run 10:45 or 10:30, right? And what are we going to do today? We are going to do in series the exact same thing as we have done yesterday. At least the second part we are going to do in theory, natural language processing and machine learning. In practice, it will be completely different, right? So we will run code. I try to run, even though we are doing different things, always the same code. And if there is one thing, or I really try to make it as, let's say, repetitive as possible, since at the end of the day, machine learning should be as repetitive as possible. What we will learn today is a library, Scikit-learn, that will allow us to do most of the machine learning techniques that you need in a very well and nice way. And that library works with objects that we started to get acquainted to yesterday. These feature matrices that have the features there inside. We remember that we learned something about TF-IDF, about bag of words that turns documents that have a stream of words inside with an order into an unordered bag of words. And that bag of words lives for the computer in these matrices. These matrices have for each document a row, and each feature, typically each word or each n-gram, is represented by a column. And the cell of the row and the column tells us how many times a word in that specific document occurs. And a word, the specific word in that column, and document, the specific document that's represented by that row. But before we go so deep into it, let me just give a slight overview about, in general, what machine learning is. So yesterday, we had our repository, our shared repository, and you all seem to remember that repository, right? So you all have it open right now, right? You have it open. And in that repository, you will find a new folder, Intro to ML, Scikit-learn. And there's a link to slides. Can we just we can actually look just at the slides here. They are just for your later convenience. Let's just see if we can turn it into some full screen thing. Oh. So that would be the welcome thing, first of all. So what is machine learning? Is something we are going to tackle a little bit. And we have already seen it's basically a field of study that tries to go away from the idea of explicit programming, but using examples to optimize a program with respect to some certain output. And we have seen some different, more operative definitions. But what I would like to do today is, at least if there's one thing, I would like to really go to the idea that machine learning is at the end of the day always the same. And we have yesterday heard something about dimensionality reduction, and there is a... I'm not sharing my screen. I hope that would be done by my machine. Why are you not sharing the screen? What is shared? Okay, let me see. but which is like the green. Thank you. Okay. So can you now see the screen? Is the screen available? Is the screen now available?
Which one? They are not available. Go to the screen share.
Okay.
You
It's just-
are on this one.
Yes.
Huh.
But I'm gonna need the whole screen.
Yeah, you can switch the screens later.
Okay, fair enough.
Yes.
But now you can see it, right? So I would like to really go to the idea that machine learning is at the end of the day always the same. It's a form of dimensionality reduction. We potentially high dimensional input space into a very low or low dimensional output space. Sounds fancy. What it is. What is it? So that really means, like for text mining, in a document, there is a high number of words. That's our high dimensional input space. And we want to have a low dimensional output space. It's typically what the document should be. It's like positive, it's like negative, it's like spam, it's like non-spam. It's like some dimension we would like to measure, for which we have some training examples or not. So there are two things in it. It's a dimensionality reduction from typically a high dimensional input space to typically some low dimensional output space. And that dimensionality reduction can be expressed as a function from a high dimensional space to a low dimensional space. And that function needs to be trained. Training means like parameters. So that's between that dependent variable, that output thing, what we observe and what the function is predicting, all is possible. And the microphone is already a little bit like backing down. That doesn't really matter. So how do we really like learn that in quotes? Supervised and unsupervised. Supervised is the word where we have, for example, for text mining, where we have training labels. Training labels like spam, non-spam. That means, let's say, we have 1,000 emails. These 1,000 emails are represented as a matrix. How big is the matrix? Does anyone would like to have a guess? How big is a matrix that can represent 1,000 emails as a document term matrix? How big would that be? To know something. How big could, for 1,000 documents, like would be like document term matrix, how big could that be? Hundreds, so that would be our book, right? Our features. That would be like 100,000, and for 1,000 documents, how many rows are we having? So 1,000 times 100,000 would be our feature matrix. And with that, we would have now, if we have a supervised setup, and we have like a dependent variable, that's something like spam or non-spam, that would be a vector. How long would that vector be? Yes. So for our supervised setup, we have X feature matrix and Y, our vector of dependent variables. And these things need to match. We need to have as many labels as we have documents. So each training data point actually consists of two things. X, the independent stuff, the word, the document term, or the vector representation, for example, document, and Y, the dependent variable. And we want to learn that function between X and Y and optimize the parameters so that the distance between what we predict with that function and what we actually observe is minimized. Sounds crazy, I know. But that is as horrible as it gets. And from now on, it only gets simpler, since supervised and unsupervised are more or less the same. So that whole diagram there basically says, in the supervised world, we always have these XY pairs. We have for every document, we have the dependent variable in the training phase. And we optimize that function. For the unsupervised, you can think like they are actually more or less the same. what would be the unsupervised counterpart to it? It just means that we have only the document, only the Y, only the representation of the word in the vector space. And if I say vector space or bag of words, or that representation that V dimensional, where V is the number of items or words in our vocabulary for a document, these are all the same. So it's basically a matrix, document term matrix, that represents our document. And for the unsupervised case, that's all we have. And learning in the unsupervised, okay, what would that be? Like if we would, in the supervised case, if we would have some labels such as spam or non-spam, what would that task be in the unsupervised case? It would be basically telling or asking the computer, can you come up with labels in such a way that the average distance in the vector space between the documents that are all belonging to one class is minimized. So in other words, all the documents within one class should be more or less talking about the same thing. And all the documents that belong to different class, so every pair between between classes of documents, the distance should be maximized. So in other words, if you pick a document from spam that should be as different, or from one category that should be in the content as different as possible as a document in the other class. So let me just have a sip of coffee. So what we are really taking away here from that diagram is that all of that machine learning, or at least the way how we approach it today, is basically operating on a matrix. And the difference between supervised and unsupervised is that for the supervised case, in the learning case, we have a vector Y that gives us basically the labels we want to have. And in the unsupervised case, it's basically telling or asking the computer, can you make up the labels as well? And that means different things, like, can you say which document belongs to which label? And can you even maybe guess, like, how many different labels there should be, right? So there can be there might not just be one category difference, like spam or non-spam. There might be like, in the unsupervised thing, some of you might have heard of topic models. There might be the question like, how many topics would be appropriate to represent my corpora? So only XY pairs during learning. That answers the question, what belongs to what in the categorical sense. That answers the question also, what would be the same as what else? But you need supervision for that. You need to have the training you need to have the Y for the training. But there's one further thing that you can differentiate. Yesterday we talked about classification, but there is something very, very related to. And classification, first of all, what is it? It is a discrete output variable. So that's spam or non-spam. It's either or. But we have also like float variables, so continuous variables, and that would be regression. So what we are doing, but it's also like very related. You can go from a regression to a classification by just sending that to a so-called link function. And that makes basically a decision above a certain threshold of that continuous output of that regression. It would be a spam or non-spam. And for the unsupervised case, where we do not have the Y labels, what would be the difference there? The difference would be their clustering, where the computer has to come up with these categories, spam, non-spam, and it just comes up with its own categories that maximize the distance between the clusters and minimize the distance between the the data objects within one cluster. And but for clusters are discrete. And in the unsupervised world, there's also like a continuous case where you have these continuous Y variables for which you do not have any training examples. And that's basically called dimensionality reduction or scaling, where each data point is represented by a continuous single dimension or multiple dimension as in topic models, for which you do not have any training examples. right? So, and that's what really a lot of people, for example, like with these unsupervised methods, like topic models. You can just put your stuff in your machine. Do not need to have any training data. And what comes out is always like technically working, right? You can't go wrong with that. And yeah, one important thing here about is like that is all the theory, at least I know more or less. And I promise it will not get any more difficult. But how does that now relate to code and to the code you will see? So we've talked about three concepts here that can be used to think about that whole classical machine learning space. And even the deep learning world can be described in a very similar way. Since at the end of the day, it's also learning functions, right? So it's like you have that high dimensional input space, potentially a photo of someone, and you want to know if that photo is someone like who is happy or not, right? So you have a photo, that's a matrix. You can unroll that matrix into a vector. Very naively, will not work that simply, but you could do that, and then take just the gray numbers. So you have a feature representation of a document. And then the question would be, can we go from that high dimensional input space to a one-dimensional output space? And that would be in the case of finding happy people, asking that function, is that guy happy or not happy? Right? So it can be used, the idea of functions that do that transformation and typically reduction of dimensionality can be used to think about classical machine learning, about statistics, and it can be used to think about advanced deep methods. One slight difference is just that for the deep methods, it's typically not just that X and Y, there's just one function in between, but there are stacked multiple functions. So the Y's of the first layer will become the X of the next layer. That's a big difference there. But it's also like hard to interpret there. But what are the concepts we are really needing to think and for the computer to compute with these X data, Y labels? We need these functions, and these functions will be, that's one important thing we will learn. They will be our model objects, and these model objects are presented in the supervised case with these XY pairs. So the first thing what we will learn is like how we can create such a function. That's just constructor called. The next thing is how we can teach the function something. That means not exactly programming what the parameters of that function should be, but give that function these XY examples and say, please, can you optimize your internal parameters so that the predictive outcome of these Y variables, if you would use your parameters between your predictive outcomes and the actual observed training data is minimized. So we need the constructor to create these functions. We need a function called fit. And that function fit takes two things. It takes X, our feature matrix, and it takes Y, our label vector. And these things need to match in dimensionality. So we need to have as many labels as there are documents, as there are rows in our X matrix. So we need to have a constructor to create that function, that model. We need to have the fit thing that optimizes the parameters of these functions. And once we have optimized the parameters, let's say of our function that should perform the function of spam classification, what are we to do next? Let's say we have a new data object, a new email just arrived. What are we going to do next? What are we want to do next? You not? So what would that be? What you get a new email? What would be the proper question you could ask that thing? Yes. Okay. So you want to do a new prediction, and you want to predict, given a new X vector, what would be the best guess given the parameters of the function for a Y? What would be the new prediction of is it spam or not spam? So that's what you would do. And thank you. And so technically, that means we need to turn that email, which is first of all just a document, human readable. We would need to transform that again into our vector space, into our bag of words representation. It would be sent a vector, and that vector would have the dimensionality 1 times number of different words in our vocabulary. 1, since it's one document, and number of different words in our vocabularies, and these are the features we are using. If you would import 10 emails, it would be 10 times number of different words in our feature matrix. And our predict function is a function. So our fit function was a function that took X and Y as parameters. And that was for fitting, for training, for learning the parameters. Our predict function takes only Y, that 1 times v-dimensional matrix, or 1 times v-dimensional vector in case of one prediction, or D for number of documents times v-dimensional matrix in terms of we want to predict labels for multiple documents. And then we have that predict function that takes this input X of newly observed data points and gives us, in the best case, if everything went right, a new guess for Y. So these predicted labels that should now inform us, is that a spam or not spam? And that's basically the whole setup what we will do today. We will create out of documents these X matrices, feature extraction called, and we will instantiate different types of functions, different types of models. We will fit newly XY pairs for these models, and we will predict new variables Y. That's for the supervised case, and for the unsupervised, we would just do the same, but not show the Y. So it's basically just a dimensionality reduction with the best case.
Yeah. For the classification, you mean that we should try the different algorithms, which gives us the minimum loss or discrepancy between the predicted and the actual Y's, you mean?
Yes, so that's actually a very good question that tells me that I'm actually far too slow and you're far too quick, since that's where we want to go. And we can even ask ourselves, given a multitude of models, what would be the best model? Or we can ask ourselves, if we have different models, can we average above these through these different models and say, can we reach some sort of consensus? Maybe there's one who's not guessing the same, but maybe we should still incorporate a little bit in our results. So there are different ways to do that. And model averaging, selection, which would be the right model for a given data set, which might differ. Those are actually the advanced and absolutely right questions to ask. So we said that. Okay. Yeah, so I mean, there are different ways you can pick the best ones, but I have to caution a little bit with picking the best things. Just let's make a very simple example. Let's say you have an almost fair coin that comes up that has a probability of, let's say, 51% head and 49% tail. So nothing funny about that coin. It's never really going to be perfect, right? And then you would have to predict a site that coin comes up that maximizes our expectation. In other words, that's the most likely, and for 51% head, 49% tail, what's it going to be?
Head.
Head. And it will always be head. Since if you are saying like, what's the best thing there? And the idea would be that if we train our model on these so-called empirical distributions, like in this case, if we would always take the maximum, that would be head, head, head. And if we train our model, that parameter of the model should recover as much information as possible from the data. And if we would just use always the best or the most likely prediction, the maximum likelihood prediction, and if we would have a coin that comes basically 51-49, always head, 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 our expectation of what that coin's behavior would be basically 100% like head and 0% tail, and that's not what the coin is. And so just picking the maximum would be one way to go, but might not be the right way to go. The other, for example, would be you have a very small data set and you have no evidence for example, you have just observed where the sun is like during the day, one day, and you have all that information, and then you fit the maximum expectation to your model and ask yourself, will the sun ever go down? And you've never seen that. The answer would be no, it would be 0 probability. Obviously not the case. So you don't want to do like, you don't want to just optimize the model. You will have some prior uncertainty inside there. But let's just go a little bit into the code so that we are not as abstract and incorporate one further question. Yes, yes. So there are obviously, I mean, like what you can really think about, like, is the output variable, the y, is it continuous or discrete? It can be continuous for the and discrete for the supervised case. Continuous would be regression. Discrete would be typically called categorization. And the thing is, like, there is like a language, like it's not really 100% sure. There can be, for example, the logistic regression, right? That has that categorical output, and its name, it suggests like regression. Okay, that's continuous. But technically speaking, it makes sense to separate what the output variables are if you want to do that. And one good distinction would be, is it continuous or is it discrete? And the other good distinction that's really informative about like what type of model you're speaking about is are you having any training data at all? If you're having no training data, that would be basically the question, like, and for the continuous case would be, can you extract from a document corpus one dimension that sorts all the documents in the best way? Political scientists know that quite well. It's called an ideal point model. It basically says, like, given the document collection, what would be the major dimension that separates all these documents to the best divide? And some people argue that would be the left-right dimension. But anyway, that would be the unsupervised case. And for unsupervised continuous and unsupervised discrete would be, can you cluster it? But let's just go to that page. And since we have spoken so long, or I have spoken so long, let's just use an online version this time. You can start that by clicking here. And it should give you over to an interactive version of the Jupyter environment we have enjoyed yesterday already, and hopefully everything will be installed. So that environment is a newer version of what we have seen yesterday. So it ends with something called lab. You could go back to the version we had last time if you change the URL ending lab into tree. But actually the newer version is quite nice as well, since it looks like a classic IDE, Integrated Development Environment. And it has on its left side the overview of folders. And one folder is called Intro to ML. And that's the folder we are working on or in today. And part one would be the part we are starting with. And there's one further thing. You have here something, an online environment where you do not need any authentication. So that environment will have a timeout where it basically times out after 10 or 20 minutes, I think 10 minutes of inactivity. And to avoid that, we need constant activity. And the best way to do that is to click in our launcher on the terminal thing. I will repeat that so that everyone can follow. Click on the terminal thing and type htop, H-T-O-P, and gives us an idea about what's going on the server. And it also keeps the connection open since it all time needs to refresh what's really going on there. So first thing, did the repository start for everyone? Is everyone seeing the Jupyter environment? Can I see a show of hands just to make sure? For 1 person, 2 person, it works, 3 person, 4, 5, 6. You guys over there, it works as well? 7? Okay, once it has started, you go to the launcher. If the launcher is not around, you can open the launcher by clicking here. No, you cannot do that. You click actually here. And then you open up a new terminal. And in that terminal, you type htop and should get then an interactive idea about what's going on the server. Does that work for everyone? If it does not work, your server will go down after 10 minutes. So HTOP is what you need there. And if everything works out properly, it should look like something like that. Does everyone have htop running? Everyone htop running? No? Why not? Okay. But I see help is on the way. And you have PyCharm, I know. There's no htop in PyCharm. Make sure you have it running. Some people will go around and help you so that we get all of you going. So you have it working? Is it working over there? You get it? Why not? Yeah, so that's a perfect. Yes. Yes, you have to Control C. Control C. And now, yes. And yes, now you take htop. H-T-O-P. Yes, that's perfect. And working. So it works for everyone. And which really relieves me. Can I see also a show of hands for the online people and see if everyone got it to work for the online people? And we have someone who is also watching a little bit on our participant. Are we having a positive feedback there with a show of hands? Are we having a positive feedback from the online people with a show of hands? Are we having that? Are we having a positive feedback from the online people with a show of hands? No? Maybe you can ask them if they can do that or if there's an issue. So, but let's just assume that it would have worked out for everyone. We remember from yesterday that obviously all we need to do is click one of those notebooks. We start with part 1. And in that notebook, part 1, we have our friendly and kind Jupyter notebook that you all know, now set up with content and with the right dependencies all in the cloud. And just to make sure that that works also for everyone, I'm going to the first cell, and I need someone who. How can I execute that cell again? What is the shortcut again to execute the first cell? What? Shift Enter. Let's see. Shift Enter, and there is a star coming up, and one tells me it's the first thing that's executing. Yes, thank you. So, what is the first notebook about? It's about a data set that's the most well-known data set, I would say, in whole statistics, not just in biology or those people that study flowers, but it's a really interesting data set. It's extremely simple. And the data set basically describes flowers, these iris flowers, and there are 4 different irises, 4 different types of irises. And these irises, each individual flower, is described by 4 different measurements, empirical measurements that are taken. Someone is to these individual flowers and measures the size, the length, and the width of these petals and sepals or so. I have no idea what that means, but basically someone sees how many centimeters is it wide and has length, and these things. How are they wide? What is the length of these things? And we record for each of these individual measurement, we record the row of 4 different features. So each individual measurement will be a 1 times 4 representation, a vector of 4 different dimensions. And the data set is so interesting and so important, since it really tells not just us, but almost everyone who looks into these things, it tells us that machine learning really can be thought about always the same. It helps me to make the point that what we are doing is always just the same. We have a high dimensional input space that's potentially very, very high dimensional. The high dimension in this case is 4, right? And you want to map that high dimensional input space to some low dimensional output space. That high dimensional data, which is typically represented by X, low dimensional D. And in this case, it would be not spam or not spam, but we have 4 different types of flowers. So the output Y would be a categorical output vector. It would be length of number of different measurements we are having, different flowers we have seen. And for each flower, we would have a value there inside that tells us which flower it is. And that's all what it is. It's really about learning the relationship between X and Y. That's what machine learning is. Machine learning is about optimizing the parameters of functions so that given some training data, which is typically pairs of X and Y, we can optimize or can learn some predictions about new observations. And the libraries we are using for that is something we have seen last time already. It's pandas, which is basically some library that helps us to deal better with data frames. And NumPy is a library that helps us to work with matrices. So basically, that's a more technical representation of this one here. And then we have here some matplotlib inline. It just tells us whenever we plot something, please can you show that to us directly in the notebook and not just save it on the disk. So what am I going to do now is using that iris data set, tell you how the most important things what I'm going to show you is how can you construct that function, that classifier object. It's called a constructor. Given that function, we have it constructed, initialized. How can you fit these XY pairs? And given the function with already fitted parameters, so the trained model, how can we, given new X, new observations, predict new Ys? How can we given new lengths and widths of these sepals and petals, predict new specimens, what the type of that iris would be. And those are the most important things what we will do in that segment. And then later on, we will generalize that thing to text. And that would be in part 3, I guess. We will do the same thing for spam. We will take a document, turn it into a feature representation, and given that X vocabulary size times D number of documents, document term matrix, we will predict like, and first of all, we will learn is it spam or not spam. And for new documents, we will predict like, is it spam or not spam? So what do we need first? After we have started, we need a sip of coffee for Arnim. And we need the data. And the nice thing about Python in general is like it really helps us to work with to do complex things with one line. And what this really helps us to do is really like get data from the internet, and that's stored in that variable called df, which is typically used for data frame, but you can name it whichever way you want. But if you remain it here, you would also need to rename it down there, since if not, the variable will not count. And but we want to have you just want to. There was a question. So the NumPy library is used for the data arrays inside the pandas data frame. And in that, if we have something like a pandas data frame, you can write now df dot, and Python is proving me instantly wrong, but I would take a guess, df dot values, and that would give you back an object which is just NumPy array. So array would be like a more native representation of the data without, for example, things such as names. So it would be just an array where you would have just integer indexes, but not these comfy human language names there. But you can try it. Just try df.values, I guess. But now we have that thing. And what we need to do here is we need to take the data. That's our X part, right? That's the data, X part, and that is the Y part. There are numbers already inside there that represent these, or no, there are not numbers inside there, but these things would represent different type of flowers. And what we would need, or what we are needing to do now, is separate the X from the Y. And while X is already a number, we need to turn that here, these strings, into a vector of numbers, into a vector of integers, into something that can then be predicted by our function more easily. And that's basically the convenient stuff what we will do in the following lines. And I will just go over these things. I will not like explain everything. Typically, we would need for that whole segment at least a day. And we want to even do more. So I will just click through that, but I encourage you, and I will also distribute later on some more advanced stuff, that you make yourself, you figure out how it works and not just click shift return, since the learning part should be really change things. Ask yourself, like, for example, how can you figure out like not just the beginning rows, but the end, the last, the tailing rows? How can I get access to these things and not just shift enter? But now we will, for convenience reasons, just, and because it's also convenient for me, go with the shift enter. So here we will get some overview about like how many different specimens from each species are we having. And that is in particular important if we talk about is the training set well balanced? Do we have from every type the same number of instances there? And here we see we have a data set of total 150, and of each type we have 15 of these 3 different flowers. Shape tells us something about the dimensionality here, and now we see 5 columns. 4 is X, 4 for the X thing, 1 column for the Y. The Y is still as a string there. Separate that and turn the Y string into an integer. That's our next program. Here you see we take the X part out of it. We take the values, and then we will look at the type of the values. And that's now the representation as a NumPy array. That's and we see it here already in the type definition, right? So what's missing there is like the comfortable human dimension naming. So the next thing is we get the Y vector. And how do we do that getting of the Y vector? We select from the data frame the column species, and then get the values from that. And then let's see, and assign that vector to a variable called values and get the first 5. That's an array now, just with integers inside. And now the first encounter with that magical library Scikit-learn. And we have now already something like fit transform. It's not the real fit thing as we have later on in the models, but it is related. It will basically take a vector of labels, one vector of labels, and turn that into numbers. So we give it over, we hand it over that vector of strings, Zetosa 50 times, and then 50 times another label, and get back a vector of integers. And I will do the magic of pressing Shift Return, and we will see the first 4 labels. Does it work for everyone? Or if not, you can just restart the thing. You can just like restart it and just start also the terminal if you restart it. Okay. So what are we having now at that situation? We have now isolated the X matrix. We have turned the feature vector as the label vector that was originally human level names or human readable names into numbers, right? These human readable things has been turned into numbers. And now, slowly but steadily, we can really start to do something we're actually here for. That's our X thing, and takes that X, takes that Y, and hand over to our model. And the simplest thing there, and that's basically what we will repeat and repeat and repeat. And that's really the part, if there's one thing you're really going to take home in terms of, let's say, working with the library, it's this 3 lines here. You import some classifier, and you will have an overview in Scikit-learn about like what classifiers there are, and I will share a link with you. You instantiate that classifier. That's basically, you create a new classifier, you create a new instance of a model, and you hand over that instance to a variable, in this time CLF classifier. So now it's instantiated that thing. That's basically something that holds your parameters, so to say. And then the next thing with that function is you go to that function with X and Y and say, here, function, can you please optimize your parameters in such a way that the distance between like what you would predict and what is actually there in the Y is minimized. In that case, with the nearest neighbor classifier, it's not really optimizing parameters, but in the general case of, let's say, for example, logistic regression and most other classifiers, there are parameters optimized. And then, so first step was instantiating the classifier. Next thing is optimizing the classifier with fit predict. So giving the classifier the training data. And then the last thing would be predict something new. So giving the classifier some new data and get some predictions out of it. In this case, we predict the same data, or we predict on the data that you have trained on. So that's really like not really new data. It's like the stuff we've trained on. But fit features labels X and Y, predict only new X, not just X as in this case. But this helps us with something very, very interesting. If that stuff works, if the classifier now makes on new data predictions that are comparable to what you have or what we have seen, or behave similar to what we have seen in our training data, our predicted labels should equal the actual labels in our training data, or as we have heard last time, in our held out data. So let's just see how that works. We import the classifier. We tell basically the computer, there is a library. Here you can learn about these models. Next thing is like, can you create a model for us and train it, fit it? And a third thing is, can you predict new parameters? New predictions, new Ys. And that's all that there is. There is nothing more. What we will do, we will use different kind of classifiers. We will, or different kind of models, functions. We will use things that have not just, or could use things that just not have only discrete output, discrete Y, but also continuous Y. We could go even so far as just hand over something that has only X, no Y part, and still ask it to make some predictions. That would be the ideal point model, for example, for political communications, or for survey scientists, it would be like mapping a set of responses to questions to some common dimension to establish some latent psychometric dimensions there. So create the model, fit it, and then predict it. And now we are going to the evaluation part. And that's really the thing, like, are we making progress? If we have learned anything at all, it should mean that with showing the algorithm new data, the distance between what is predicted by the model and what actually is there, for example, that we have like manually annotated, should get smaller with new data. And how do we compare that, or how do we do that? So the simplest case is just like, we would ask, like, is the prediction the same? The predicted value is the same as the true Y values. So we take our true Y values, in this case, from the training data, and compare it to the predicted. So, but that's a little bit cheating, like it's like predicting the past. So we have shown you what the Y should be, and now you know the Ys. In reality, you would not ask the model, can you predict if a email from your training data set is spam or non-spam? But you would ask, like, I have a new email. Do you think it's spam or non-spam? But that's already like a little bit longer. So we want to have that condensed and basically ask what's the proportion of things you get right or wrong, depending on the way you look at it. And we can do that basically with this sum of things. And we have a very, very well-performing classifier. You seem to be awfully quiet, but if someone would come to me and tell me that they have an accuracy of 9.6666% probability, then I would become highly skeptical. How do we get there? Because we predict what we have shown already to the classifier. It's just like for us getting a feeling how that is. So we compare the true labels with the predicted labels, and in that case, we get 99.666 accuracy. In reality, we would compare some held out labels with the predicted labels. And then you get an accuracy typically that's much, much lower. So always, if you have an accuracy above 70%, if more than 70%, even in a binary classification thing, are right, you should know why it's better, since typically going beyond 70+%, you're going beyond 80, the dead giveaway that there's something interesting going on you want to know about. Yes. Yes, so there is basically, so what's that fit transform method? That fit transform, let me see where we had that fit transform here. That thing that has some information. It's basically a map between the string of the setosa, for example, and the number by which the specific string is represented. And what you want to look at is that map. And that map is important in this case. It has 3 different entries, different setosa and veritosa and what they are called, and as integer. In the case of larger documents in the natural language processing world, you would have for each word an entry in the dictionary. So you would have hello is 48, good morning is 325. And that thing, that dictionary object, is something we need for turning the document into the vector. And you will later also need for turning a vector representation, for example, in a topic into something where you can figure out like, okay, the first dimension in the topic is cars, and the next dimension in the topic is streets, and the next dimension driving, and the next dimension is, let's say, trees. And then you can ask yourself, like, which of these 3, 4 words that have a high probability in the document, in the topic, do not fit there, and can, for example, do some evaluations, some human level evaluations there. But yes, that dictionary is important, and you should inspect these elements, or you should always like look up the documentation. And if you go to the Scikit-learn or Scikit-learn website, you will find the API documentation, and typically also it helps just if you go, for example, Scikit-learn and fit transform, you will see what that object does. And what is also like really important is like for people starting with that thing or starting with any sort of programming, they are always asking themselves, like, there are so many new things. How can we learn? How can we remember all these things? And the simple answer is you don't need to learn that. There is like a very well-established autocompletion. No programmer knows that. I do not know what that fit transform method actually gives back. I have no idea, and that's absolutely fine since the internet knows. What you need to know is like, where can you find that information? And you need to become confident that you can start to do data analysis without knowing everything. You will learn something on the go, and make sure that you have a proper setup that does this auto-completion. Make sure that you know where the API docs are. And then you can find out how you can reverse from words to numbers and get a function, for example, that turns the numbers into the words again. And you will actually have that in the later parts of that notebooks. Okay, fair enough. So, yes. Okay. But sorry, what was the question? What do you mean with dots? So separating the object, for separating the object from a function, something like that dot, or what do you mean?
For the labels, for example, there is a label in the 7th line
labels,
that dot?
pre-processing dots, and what function the dots are generally used for in Python code?
Ah, okay. So that dot thing. Okay. It has nothing to do actually, I think, with Python. I think every programming language has some things that allow you to call methods on an object. So that's basically, that is an object. And the idea of the object is that the object has a really large internal state, but you can only access or interact with the internal state of that object via some well-defined methods. And for that, you need to tell the computer, this is the function, and here, computer, can you open now the method table? And in that method table, pick that method called this. Right? And the computer knows also it's a method because it has that parenthesis at the end. So for example, if you would have a direct access to a variable, it would not have parentheses at the end. So, but having that dots there, I can imagine that there's a programming language that uses a different symbol to do that, but I think like all programming languages do that. So, and the nice thing is also like the computer knows, or the interpreter in that case, since Python is an interpreted language, the interpreter knows like what is the method table of that object. So if you write the object name, in that case, basically it's a class name, the class thing, but still it's essentially an object. And you type dot, and the computer knows, we are now talking about the methods. It can open up the method table. And if you press the autocomplete key combination in your IPython environment, which is typically something like, I don't know what it is, Shift Enter. No, Shift Enter is for what is autocomplete? You know it? But typically, tab was the thing I was searching for. Yes, you can get all the methods that there are available that start with, for example, the letter L or any. So you could just type processing dot tab, and you should see, for example, the whole method table. And the dot is just methods. Okay, but good question. It was at least a nice excuse for me to get some coffee, but you want me to test that now? Should I test that? But the thing is, like, that's potentially something you want to do as an exercise, and maybe you want to have with me an overview about that machine learning thing we've talked about, and utilize the time for that, and then you can later on do some programming stuff. So what have we done? We have now turned like a string vector into integer vector. We have created a classifier object, that function, assigned it to the classifier variable, fitted that model, that function, to data, X and Y pairs. That's like, can someone help me where it is? Training the models, yes. That's a function, that's our method, fitted to X and Y. Optimizing the parameters, even so that's not really, like, it's just storing actually the training data. Then we have that optimized function, and we predict new Y's, given some, in best case, new X's. And once we have done that prediction, we can ask, like, how well is the prediction doing in comparison to our held out? Remember, held out, don't do it on the training data. Don't tell anyone that I have taught you that. But how well is it doing? And we get a 150 length of 150 vector back in our case, since we have 150 examples in our training. We have 150 examples in our prediction, and we have 99 or 96.666 accuracy. That means extremely good. Skeptical. Then we turn that into something where we just have a number of 150, 140 are true. X predicted, Y predicted equals Y observed. We turn that number, which is dependent on the size of the training data, into a fraction. percentage, one might say. And after that long thing, we do what every programmer does, and that is consolidate multiple steps into one function that in the best case already the library does. And that's what is here, or no, that's actually not done, but there is something where we could, let's say, accuracy, where we could compute that completely in the using not our self-implemented stuff, but stuff that's is implemented by Scikit-learn, and that's here that thing that basically does that accuracy score. And you should test that. I would recommend that to get into that library. You can use accuracy score, and that should compute the percentage. In this case, if you would apply it, it should return 0.9666. Okay, fair enough. But I've told you that you should not, you should actually, or we have heard also the last time, we should only use training data for training, and we should not use held out data for training. So we first need to do that split thing. So imagine just you had your student assistants and they created a data set, turning every, or giving you for every document a label, spam, non-spam, or politically left-leaning, right-leaning for 100 documents. You have to split that into test and training data. And that's something that there are also ready available functions that do these things. So I could go now into very detail about what that thing is doing, but I would recommend to do something different. I would recommend that you go later into the API document and find out what these different things are here. But the important part here is really the size of the test data set. And typically, like you would have a split like 80-20, or in this case, 63%. So 33 documents would be your test data set. And then you can, if you have that split, all that does, it's basically, it randomly selects out of your X matrix rows you can do training on, and it sets aside the test one. So, and that helps you to truly evaluate how well your model predicts not only data it has already seen, can predict the past, but actually can really predict the future. And what is also interesting here is like you want to give those methods that have this random picking, you want to have, for example, like a random seed there inside that helps you with reproducibility. So that each time you execute that method, it does the same split, and you can use that later on for debugging. And in that case, there is actually something funny going on. You should now, or we should now see a 1/4, 2/4 split, and these should be reflected in the lengths. And we have, by the way, lost our connection here. Let's just see if it's still there. No, we need to. Okay. Yes. So let's see that split, and now we should see 2/3 training features and the according properly matched labels, and these are the X parts, and that would be for the held out part. And now we can do the same game again and do the accuracy testing with or train a model on only the training data. And then we have to do again the same thing, get the classifier, fit it, and then do some prediction. And those are our predictions for the 50 one. Now that should be, if you do that, that object should be a vector of length 50. Should only use X test to infer new y test from x test, y test. And with these things, we can now ask ourselves, like, what is the training accuracy? And that's our new accuracy sum here. And we see it's surprisingly high again. And we're almost over, right? With the time. And you can use some ready-made functions. But there's one more thing. So let me just recapitulate what we have done, since we are nearing to the end here a little bit. What I try to do is introduce you to a notion of natural language processing that's actually machine learning. In natural language processing, the traditional way we use a representation for documents that's called bag of words representation, where the order is forgotten, and each document is a vector representation in that vocabulary space. And each document that a human can read is then represented by a vector that has as many dimensions as terms in our vocabulary. And that is a science in itself to pick the right vocabulary. Every political Qualcomm topic model paper that claims that we have now found some true and repeatable results, the magic is always in like which words you put in your vocabulary. But anyway, you turn these human level documents into vectors. It's not just one document, but multiple documents. So it's a matrix. The matrix is always like numbers of documents times size of the vocabulary. That's your document term matrix representation. That document term matrix representation can then be used to train a function. And that function would be basically mapping that X matrix into a high X with many different words in vocabulary to a low dimensionality reduction Y. If you have training Y is a supervised task, and the task would be to optimize the models as the parameters of the. That's the difference between predicted Y in the training data set and the observed training test. And the theoretical assumption there is something called exchangeability. That means what holds true in your training data set holds also true in your headout data set. And so you have learned something meaningful, and you have done something that's typically referred to as separating signal from noise. So much of that learning part is really like trying to find a few parameters that kept statistically interesting parts of our relationship we are interested in, like between, let's say, something left-leaning or right-leaning, which are the discriminating features in the bag of words model which would be the words that are most informative if something is left or right-leaning. And you want to have a model that has only a limited number of features, limited number of parameters. You want to have a model that has not 100% accuracy on the training data set, since you want to separate with that limited capacity for information in the model. You want to separate the signal that's always there from the noise. And that's what really, what also makes it statistically interesting. These things, it's not just about prediction, it's about finding similarities, general patterns in your training data set. So if we have set Y's for our X, it's a supervised thing. If we have Y's and those are discrete, it's a classification. If we have Y's and they are continuous, it's a regression. If we don't have Y's and they are discrete, it's clustering. It's basically, there's the data, figure out what would be the proper groups. If we do not have y's, and they are not discrete but continuous, it's called dimensionality or scaling, also referred to as dimensionality reduction, but typically scaling. And in that scaling world, we can have a one-dimensional y for a v-dimensional x input, so classic dimensionality reduction from a v-dimensional vocabulary space to a one-dimensional output space. But for those that are interested in political communication, it's not just the one-dimensional ideal point thing or the one-dimensional thing that is interesting in our scale, but there might be multiple dimensions, and it's not called mapping a high-dimensional space to one dimension, but it's dimensionality reduction. So low dimensionality could be also achieved with something like with a topic model. So mapping a high-dimensional input space, that X matrix for the documents in the vector space, B times V, to a low-dimensional representation that's not one-dimensional, but for example, k-dimensional, where k is the number of different topics. And that basically should give us a complete overview about what would be considered classical machine learning and very simple statistic. What the main things that we will now, or what you will do if you want to work with that library, and I think the nice thing about Scikit-learn is that it gives a unified framework for working with so many different things. From there is like part 3, you will have supervised work with text. Part 4, you will have the unsupervised work with text. And it gives you really always that unified thing. Create that model object, instantiate the model, then fit something with these X matrix and Y matrix, and then predict something. Fit first and predict then would be the supervised case. For the unsupervised case, you would first use something that's called, I guess, fit predict, fit underscore predict. But you still could use for the unsupervised thing, poorly prediction. So imagine you would have an ideal point model learned on text. You did that fit predict, so that learning of the model in the absence of Y values. But you could then ask, like given some new documents, where on that latent dimension we have extracted, would that new document be sit without changing the parameters of the model? So I think we are almost there with 90 minutes. I can tell you that I am very thirsty, but some of you might have questions, and that could help us to conclude a little bit. Yes.
We have so many features for this example. Do we need to add a dimension reduction step here?
So let me see if I understand that question. Would there be different kind of models, concrete implementations that would be better or worse suited for different sizes of data? Where for size would refer not only to the number of instances, but also the dimensionality of the input space. And the answer would be yes. So the real thing of the different kinds of implementations, and we have yesterday heard these things like sparse matrix implementations might be helpful. Then there are like things that might automatically prune, let's say, uninteresting features. In the supervised case, that would be things like lasso, and classically known that basically gives us only a relationship between features that have a that explain a high variance in the dependent variable. So yes, there are different models that help you to find, for example, automatically what are the interesting features and the uninteresting features. For the example, like in the text mining case, there are words, and that thing we have in that, if you look up part 3 here, you will find that implementation for the TF-IDF we had yesterday, but words that occur uniformly in all documents. Uniform means there is almost no variant in which any kind of target variable explained with that thing. And these words are function words. And this there doesn't really tell us if we are left or right, or if that's spam or non-spam. It's always uniform there. And there are ways to automatically get rid of these X dimensions that have no informative things there already as part of the pre-processing. And there are like ways to regard it as part of the model. That would be something like lasso. Yes. So it depends on what you want to do. And yes, would be the answer. Any other questions? If there are no questions, that means I'm a bad lecturer. You have to make up that for yourself if you can live with that. Yes, I'm glad that you asked a question. What is the question? Someone hasn't listened. Okay, what is there anything else? If not, I would assume that you're just looking for the break. What we can do, or what I would say, that anyone who wants to work with Python in natural language gets at least a little bit like familiar with that library. Scikit-learn is the library. It's not the best library for a specific task, but it's a library that can always help you a little bit. If you want to do topic models with Python, I would recommend that you use Genzim. It's a different library. It works completely different, but you would have to learn it specifically. But if you want to just try out topic models, you can do that with Scikit-learn. If you want to do only regressions, there are special libraries for that. If you want to just try it out in a comprehensive framework, Scikit-learn is the thing. So I would recommend that you get familiar. I would recommend that you look at this TF-IDF features extraction thing and different implementations for that. And there is an example here that works with, I think, basically what we had last time, that works with a spam example. And I would highly encourage you to try these things out. Yes. We will have a break. That's the question.
This library is balance of the class automatically. So I was wondering what was the name of the method, because I heard the name before now. I can't remember.
There are things that can rebalance you. In that case, the version we've used is just uniformly picking stuff. And if we have 3 classes, 150 in total, 50 of each, so it's balanced. And by uniformly picking, the idea would be, I guess, that the test train split would be balanced as well. But there's a whole science behind that. For example, for like, imagine that there is like, for example, you have like an image classification task for cancer, not cancer. You have like only 50 cancer images, but 10,000 non-cancer, luckily. And you still want to have like detect every cancer case, but still the classifier would do best if it would always naively, never even like doing any computation, predict non-cancer. So the question that you're bringing up with a proper balanced training set and also for the testing is extremely important, which would not even try to claim that I understand it fully, since it's stuff, I guess.
Even if it's 30% imbalance, like it's the ratio of that.
In that case, we were using, it keeps the ratio of the original data set and it just splits it. That's the one but there are obviously ways you can rebalance it, reweight it, and yes. Okay. Thank you. We will see each other after the break at, when are we back? 11. Okay. So see you at 11.